In this video, I will determine the eutectic point of the sodium-potassium alloy, given the melting point and enthalpy of fusion of these two metals. So first, I'll write out this equation so we can have solid sodium. This is a fusion process. However, when we have an alloy, it's going to be this. This sodium, indeed it's a liquid, but it's actually a part of the solution. And this solution is the sodium-potassium solution. And you can say it's an ideal solution because the chemical and physical properties of sodium and potassium are very close to each other. So when you write out this physical process as if it were a reaction, we can write out this logarithm of K2 over K1 is equal to negative enthalpy of reaction of R times 1 over T2 minus 1 over T1. Why is that? Well, we're treating this as a chemical reaction, and for a chemical reaction, we have this equation. I proved this equation in some other videos. And what is K for this physical process? So for this K, it's going to be just X of sodium on top. And on the bottom, you have pure sodium solid. So it's going to be 1. And then it's going to give us this equation, X sodium over 1. So that's pure over here. X sodium is 1. So we have, again, two reactions here. One, we have pure sodium on the right-hand side. And in equation 2, we have sodium in a solution. And therefore, the mole fraction of sodium here is less than 1. And over here, I'm going to replace the enthalpy of reaction with the enthalpy of fusion. And over here, I'm making two assumptions here. One is the enthalpy of fusion of sodium is the same, whether it's pure sodium or a sodium-potassium alloy, based on the ideal solution approximation. And 2, I'm assuming the enthalpy of fusion of sodium does not depend on temperature. That means I'm assuming the heat capacity of solid and liquid sodium are really close to each other. T2. T2 now is the eutectic point we're going to have to determine. And then T1 is corresponding to the melting point of pure sodium. So it's 371 Kelvin. All right, I'm not putting units here. I'm going to just use SI units for all calculations. And now we have another equation for potassium. Similarly, we have, this is for sodium. And then we have R delta H fusion for potassium. And we have eutectic point. Look, eutectic point is the temperature both sodium and potassium. They both melt at the same temperature. So that's the definition of the eutectic point. And let's see, 337. All right. So you can compute the melting point of sodium. It's 98 degrees Celsius. So you need 98 degrees Celsius to melt sodium. You need 64 degrees to melt potassium. But later you will see if you mix sodium and potassium, you will get a much lower melting point for both metals. All right, so we got these two equations, and I hope you realize that when we have a binary system, the mole fraction of sodium and the mole fraction of potassium, well, if you sum it up, it's got to be 100%. So that means, well, over here, e to the power of negative r, this is the enthalpy of fusion for sodium which is 2.6 kilojoule per mole. Okay, and then I'm going to replace this eutectic temperature with X. All right, so I'm going to solve for X. X is the reciprocal of the eutectic temperature. It's just easier to solve the equation. So what I will do is I will just get rid of this guy. I'm going to just use X. So I will solve for the reciprocal of the eutectic temperature first. All right, so this is X sodium. What's the mole fraction of potassium? It's e to the power of negative 2330 over R times X minus 337. All right. Over here, 2.33 kilojoule per mole, 2.60 kilojoule per mole are the enthalpy of fusion of these two metals. So now we can see the equation we actually need to solve is this. Plus e to the power of negative. So these two exponential functions are the mole fractions of sodium and potassium. So it's going to be 100% or just 1. All right, and then we enter this equation in Wolfram alpha. I need to see the melting point 371. And then I'll copy the same expression here. The same expression is used for potassium mole fraction, except the numbers are different. And I will solve this equation. Doing the calculation, we got the value of X. X is 0.005712. $5172. And then we get the eutectic point. The eutectic point is the reciprocal of X. I'm going to use Google to do this calculation. Uh, 193 Kelvin. Or negative 193 minus 273, it's negative 80 degrees Celsius. So theoretically, if you have sodium and potassium alloy, if it forms an ideal solution, you're going to get a melting point much lower than 0 degrees Celsius. This is striking, but what if we look at the experimental data? So now I'm going to show you experimental data. Sodium and potassium alloy, I would recommend you to just Google sodium potassium alloy. You'll see the melting point can be as low as negative 13 degrees Celsius. Not as low as negative 80, but this is also below the freezing point of water, so this is quite surprising. And also, why such a big difference? Over here, this is negative 13 degrees Celsius. From our calculation, it's negative 80 degrees Celsius. Why such a big difference? There's such a big difference because over here you can see, if you look at the sodium liquid phase diagram of sodium potassium, well, it's not really first, it's not really an ideal solution, and two, well, it's not a simple binary phase. You have a sodium potassium co-crystal being formed in the middle. So when you have 50% of sodium and 50% potassium, they may form a new solid phase. It's different from pure solid sodium. It's different from pure solid potassium. So for this reason, our calculation result deviates from the real experimental results significantly. So we got negative 80 degrees, and over here it's negative 13 degrees. But still, I showed you both theoretically and experimentally, it's possible to melt this sodium and potassium below the freezing point of water. All right. So I'm going to put literature value here, which is negative 13 degrees Celsius. There's one more thing we need to calculate. We need to compute the eutectic composition. Over here, we're going to just use either equation. Use this equation or this equation. I'm going to use the sodium equation. All right, so if I use the sodium equation, we'll see. Sodium is negative 8.314, 2600, and then X is 0.0015172 minus over here, and then whatever the result is. I'll again enter this equation to Wolfram alpha. Okay, Wolfram alpha. Okay, this is the mole fraction of sodium, 0.461. We can also compute the mole fraction of potassium using the second equation for potassium. It's just we need to use the enthalpy of fusion for potassium and the melting point for potassium. A 0.539, and then we can double check. All right, this is good. We got a sum of 1.000. Okay, that's good. So this is the mole fraction of sodium. This is the mole fraction of potassium. But again, if we actually look at the experimental result, if you look at this picture, you can see in the middle, it forms this sodium-potassium co-crystal. So it's I think it's just it looks like just each sodium is surrounded by several potassium, and each potassium is surrounded by each sodium instead of pure sodium or pure potassium. So in this case, the experimental data are quite different from our prediction. Okay, over here. So you need to actually use this phase diagram, okay, to compute the eutectic point. You're going to have to assume this eutectic point over here is the melting point for both potassium and for this sodium-potassium co-crystal. And then you'll get a more accurate result, all right, for the eutectic point. But over here, overall, I showed you how to compute the eutectic point, including the eutectic temperature and the eutectic composition theoretically.